Hello and welcome. So we've already discussed decision trees. What's next? Well, when you know trees, the next thing is forest. And not just any forest. We are talking about a random forest, which could be quite a dense forest. Let's understand this. How does it work? So you can imagine a forest is made up of trees. We can talk about our kind of trees like these, which are inverted. We have multiple trees which are going to be used for making decisions. These are also called ensemble models. The word is ensemble. Ensemble means we are making a decision not just based on one model, but we're using multiple models to arrive at a decision. So in this case, each tree would participate to decision making. But then the obvious question that arises is, if all the trees are identical, what's the point making a decision based on their board? Because all the trees are going to give us the same conclusion. So this is what we need to break. How do we ensure that these trees are different from each other? We also say that trees are less correlated, which means these trees are not necessarily in agreement all the time. They have a difference of opinion, and that is what makes your model stronger. So how do we ensure the fundamental structure of the tree stays the same, right? So you have the same concept of a root, you have the same concept of the leaf and the nodes and everything else, exact same logic as decision trees. But instead of one tree, you're probably using hundreds of trees together. And that's why we're saying it is important to ensure that these trees are not identical. They come with a bit of a difference. Two things that we do to ensure that these trees are different from each other. First is called random space. Here we select a subset of the original features and not all the features. So if the features of the tree itself are changed, then obviously the tree would look a little different. That's the first thing that ensures that these trees are not all identical. And the second thing that we do is called bagging, which is a short form of bootstrap aggregation. This is a very popular sampling technique, which is sampling with a replacement. So let's say we started with 10,000 observations. We are saying we will create each tree using maybe 10,000 observations only, but these will not be the same observations that were originally provided to us. From within those observations, we will make our samples with replacement. When you select samples with replacement, there is a chance that certain observations will be repeated and certain observations will be excluded. What's excluded is called out of bag, and what you include in the sample is what you train your decision trees on. And then you populate them into a forest. So for each tree, the data that is being used to build a tree is being selected with replacement. So there are differences in terms of features through random space, and there are differences in terms of data. And that leads to somewhat different trees. Once again, in terms of assumptions, everything is great here, just like decision trees, because the fundamental unit of a random forest is just a tree. Pretty intuitive. So if the assumptions are identical, the cautions would also be somewhat identical. Trees in a random forest again require pruning. So those hyperparameters that we talked about in case of a decision tree would be equally applicable here. And random forests, just like decision trees, are also likely to overfit. So we have to be very careful while pruning the trees. Plus, there are certain other checks that we have to perform. For example, we have additional hyperparameters like max features. This determines the number of columns or number of features that we're going to use, something that we just addressed as random space sometime back. And n estimators, because you're creating multiple trees. So you also have to pass another hyperparameter, how many trees you want to create, 20, 50, 100, 200, you have to control this. Now, depending on the kind of choices that you make here, a random forest could take a lot of time. A lot of people lose their patience when they're running random forests on a complex data, or when they complicate the input hyperparameters to an extent where their systems almost freeze. So you want to be careful about these things when applying random forests. We'll see more of these when we start working on the hands-on piece. So with this, we conclude our video. Hope you got some clarity. Thank you.